You know that feeling when your phone gets kind of warm after you ask the AI something tricky?
Oh, yeah.
Well, that heat is like just the tip of the iceberg for this huge hidden energy problem in AI right now.
It really is. Running these big deep learning models takes a massive amount of power. Almost. Unsustainable, really.
Yeah, like some kind of sci-fi energy vampire hiding in the cloud.
Huh, exactly. And the thing is, these cloud data centers are already guzzling electricity. If
Mhm.
we keep throwing every new AI task at them, well, things are going to grind to a halt.
So we hit a wall, power-wise.
Pretty much. We need AI that doesn't need a whole power plant behind it. We need high efficiency, low power hardware,
Mhm.
especially for stuff that needs to run locally on the device itself, edge computing.
Right, like the Iron Man suit needing that little arc reactor, not a giant generator.
That's a good analogy. We need something potent but compact. And that's our mission for this deep dive.
We're looking into some really cool research that might have cracked this exact problem, making powerful AI run efficiently, right there on the edge.
hmm The paper we're digging into is called Two Orders of Magnitude Reduction in Computational Load Achieved by Ultra-Wideband Responses of an Ion Gating Reservoir.
Quite a mouthful.
It is, but the core idea is huge. This came out in ACS Nano in 2025. It's from a team primarily at NIMS, the National Institute for Material Science in Japan, and also the Tokyo University of Science.
And who are the key players here?
The lead authors are Daiki Nishioka from the International Center for Young Scientists at NIMS, and Takashi Tsuchiya, who's affiliated with both NIMS and the Tokyo University of Science, plus their colleagues Hina Kitano, Wataru Namiki, Satofumi Suma, and Kazuya Terabe.
Okay, so what's the big headline claim that got our attention?
Get this. They've developed a new device, this ion gating reservoir, or IGR, and it achieves the same kind of accuracy as deep learning models,
Okay.
but it slashes the computational load by 2 orders of magnitude.
Whoa, hang on. 2 orders. That's like 100 times less.
Exactly. It needs only 1% of the processing power compared to conventional methods. It's a massive jump.
Okay, how? That sounds almost too good to be true. How does this IGR thing work its magic? That's what we need to unpack.
Right. Let's get into it.
So before we dive into the IGR itself, let's just quickly reset the stage. We need edge computing running AI locally. Why can't our normal computer chips, the silicon ones and everything, just do that job? Why are they falling short?
Well, it boils down to how they're built. Traditional chips, your standard silicon semiconductors, are fantastic for logical step-by-step tasks. Think basic calculations.
Okay.
But machine learning, especially deep learning, it's different. It needs tons of parallel processing, really complex, nonlinear stuff happening all at once, like how our brain works, sort of.
Right, not just one calculation after another.
Exactly. And when you try to force that brain-like workload onto a chip designed for linear tasks, it's incredibly inefficient. You waste enormous amounts of energy just simulating the structure of a neural network.
Ah, so you're paying an energy tax just to pretend to be a neural network.
Oh, precisely. You just can't get high performance and low power simultaneously with that old architecture for these new AI tasks. It's a fundamental mismatch.
So we need a different approach entirely. And you
Yeah.
mentioned brain-inspired. That leads us to this physical reservoir computing idea.
Yep, that's the big conceptual leap. Physical reservoir computing, or PRC, it's totally different from deep learning, where you program every single calculation.
How so?
Okay, imagine with deep learning, you're writing millions of lines of code to simulate, say, how water flows chaotically in a bucket. Super detailed, super computationally expensive.
Right, building the simulation.
With PRC, you just take the bucket of water itself.
Literally.
Well, not literally water, but you take a physical system that has its own complex natural dynamics, could be ions moving in a gel, could be light scattering, whatever. You feed your input data into this physical system.
Okay.
And the system's inherent physics does the complex transformation for you. It processes the information naturally. Then you only need to train a very small part, like a simple readout layer, to interpret the system's response.
Whoa, so the material is the computer, in a sense. You're not simulating the complexity, you're harnessing it directly.
You got it. And because the physics does the heavy lifting, it's potentially way, way more energy efficient. You skip that massive simulation overhead.
That makes intuitive sense. Less calculation, less energy. So this specific device, the ion gating reservoir, what's the physical system it's using?
So this IGR is based on something kind of an electric double-layer transistor, or EDLT. Think of a transistor as just a tiny electronic switch. This one uses a simple structure, a thin film field effect transistor, or FET. That's good news because it means it should be relatively easy to integrate into existing manufacturing.
Okay, simple structure. What materials are key?
Two main things. First, the channel the electricity flows through is made of graphene.
Graphene, the wonder material, single layer of carbon atoms, right?
That's the one. Super thin, super conductive, and then on top of the graphene, they use a special ion gel electrolyte. Think of it like a jelly full of charged particles, ions,
Okay, graphene in a special jelly.
sort of. And then there's a gate electrode, basically a piece of gold foil. When you apply a small voltage to that gate,
Yeah.
the ions in the gel move. They rush towards the graphene surface and form a super dense layer right at the interface. That's the electric double layer, the EDL.
And that layer of ions, it affects the graphene
What is it?
somehow.
It dramatically changes the graphene's conductivity.
No.
It essentially opens or closes the switch for current flow. And the way that layer forms and dissipates its dynamics, that's what gives the device the memory and the nonlinearity that the PRC approach needs.
Okay, that sounds clever, but hang on. You said EDLTs, these electric double layer things. They've been around. I read that the older versions had a killer flaw.
They did. A really big one. Speed.
They were slow.
Glacially slow. The earlier ion-based reservoirs, they had a really narrow response range, typically slower than 10 hertz.
10 hertz.
Yeah.
What does that even mean in real terms?
It means the system takes about 100 milliseconds to react and reset. It's incredibly sluggish. Think slower than your own heartbeat.
Wow. Okay, so what could you even use that for?
Very slow processes like monitoring blood sugar changes over minutes or maybe tracking slow seismic waves from earthquakes, stuff that happens over seconds or longer.
Right, so forget about processing video or voice commands or anything fast.
Absolutely forget it. All the important high-frequency details in fast signals would just be completely lost. You couldn't track a TIE fighter in a dogfight with a 10 hertz chip, that's for sure.
You'd need ludicrous speed for that.
Okay.
Okay, so the breakthrough here must be speed then.
Exactly. This Nishioka and Tsuchiya team, they cracked the speed problem. Their device shows an ultra-wide response range. It spans 4 orders of magnitude in timescales.
4 orders. From what to what?
From as fast as 1 megahertz
Whoa, that's fast.
all the way down to 20 hertz. So it covers this huge range. And the key number, the wow fact, is the shortest relaxation time they measured.
Which was
Just 99 nanoseconds.
nanoseconds. So we went from 100 milliseconds, which is slow motion, down to nanoseconds. That's like a million times faster.
Orders and orders of magnitude faster, yeah. It's a fundamental shift in capability.
Okay, how on earth did they do that?
Yeah.
How do you get both nanosecond speed and slower responses from the same simple device? What's the trick?
It's about cleverly using multiple physical things happening at the same time within that graphene and ion gel setup.
Right.
They engineered it so there are dual dynamics coexisting.
Dual dynamics, meaning
Meaning you have 2 different speed processes happening together. First, you've got the fast dynamics. That's the really quick formation and charging of that electric double layer we talked about. That happens incredibly fast on sub-microsecond timescales, like less than a millionth of a second.
okay, that's our nanosecond speed. What's the second dynamic?
The second one provides the slow dynamics. This comes from things like molecules from the ion gel actually sticking to the graphene surface and then unsticking. That's called adsorption-desorption. And also some charge getting temporarily trapped in the underlying material. These are much slower processes.
Ah, I think I see. So it's not just one simple clock tick that's got fast reactions and slow reactions built into the same physical thing.
Exactly. And if you think about it in computing terms,
Yeah.
it's like the device has both short-term memory, thanks to the fast EDL formation.
Or quick, immediate stuff.
Right. And it also has long-term memory, thanks to those slower sticking and trapping processes.
But to remember things over longer patterns.
Precisely. It functionally mimics some pretty advanced software ideas, like LSTM networks, long short-term memory networks, which are designed to handle data that unfolds over time. But here, it's baked right into the hardware physics.
That's really clever. Having both memory scales is crucial for complex data. Okay, so they've built this thing. It's super fast. It has this dual memory. How do they prove it actually works for tough AI tasks? What did they test it on?
They didn't hold back. They threw some standard but quite challenging PRC benchmarks at it, things called NARMA tasks, which really test a system's memory capacity. But then they went for the really big challenge. predicting chaotic time series, specifically using something called the Mackey-Glass equation.
Oh, yeah, chaos prediction.
Yeah.
That's notoriously hard, right?
Yeah.
Like predicting the unpredictable usually needs serious deep learning power.
Exactly. It's a classic benchmark for complex predictive modeling. If your system can get a handle on chaos, it shows it has serious processing capability.
So how did the IGR do? Did it handle the chaos?
It nailed it. For the basic Mackey-Glass prediction, it achieved really high accuracy. They measure accuracy using something called normalized mean squared error, or NMSE lower is better. And the IGR got an incredibly low NMSE score.
Better than expected.
Exceptionally good, yes. And then they tried an even harder version, predicting 10 steps ahead into the future of the chaotic system. And there, its performance was basically on par with standard simulation-based AI models, your typical deep learning network, CNNs, RNNs. It matched their accuracy.
Okay, so accuracy-wise, it's playing in the big leagues. It can do what the complex, power-hungry models can do. But the efficiency payoff, did that hold up on these tough tests?
That's the crucial part. They measured the computational load using FLOP's floating point operations per second. It's the standard way to count how much number crunching a system is doing.
Right. How many calculations?
Yep. And when they ran the prediction part for these tasks on 10,000 data points, the IGR did it using only 1/100th of the FLOPs compared to the deep learning models.
There it is again, the 100x reduction, even on the really hard chaos problem.
Even then, 1% of the computational work for basically the same quality of result.
That's not just an improvement, that's a potential game changer for edge AI. The difference between needing a wall plug and running on a coin battery almost.
It really makes you rethink what's possible in small, low-power devices. Every milliwatt counts in edge computing, and this saves a lot of milliwatts.
Okay, so we know it's efficient, we know it has this dual memory.
Uh-huh.
But what physically gives it the raw power to handle that level of complexity? Why is it so good at processing this tricky information? What's the secret sauce in the physics?
There are a couple of key things. First is what they call high dimensionality, achieved cleverly.
High dimensionality. Sounds complex.
It just means the system can represent information in a very rich, complex way. Even though the physical device is small, they use a technique called time multiplexing.
How does that work?
They feed the input signals in sequentially, like one after another, really fast. And by doing this, they can make that one physical device behave as if it were made up of 160 different virtual nodes or processing units.
Okay. So it's like you have a small band, maybe just a few musicians.
Yeah.
But you have each musician quickly switch between playing like 10 different instruments, one after the other. So you get the sound and complexity of a huge orchestra, but without needing 160 musicians on stage.
That's a fantastic analogy. Exactly. You get high computational density, lots of processing power from a compact physical footprint.
Clever trick. What's the other factor for its power?
The other big one, maybe the most critical, is the graphene itself, specifically something called its ambipolar behavior.
Ambipolar.
Yeah, unlike most semiconductors, which are either p-type or n-type, controlling either positive or negative charge carriers, graphene is special. It can easily switch between both. Its electrical characteristic curve looks like a V-shape.
Okay. Why is being able to switch like that so important?
Because that ability to swing both ways dramatically boosts the system's nonlinearity.
Nonlinear. That sounds important for complex stuff.
Absolutely vital. Nonlinearity is basically how the output isn't just a simple proportional scaling of the input. It allows the system to create really complex mappings between inputs and outputs. The more nonlinearity, the more sophisticated the problems it can solve.
And the graphene's ambipolar nature gives it extra nonlinearity.
Loads of it, much more than you'd get from a standard unipolar device. This high-order nonlinearity is what really gives the IGR the muscle to tackle those tough NARMA tasks and, crucially, the chaotic Mackey-Glass predictions. It gives it a very high information processing capacity.
Got it. So high dimensionality from the time trick and super nonlinearity from the graphene itself. That's the combo for power.
That seems to be the winning combination they've found.
Okay, let's try and pull the key threads together from this research by Nishioka, Tsuchiya, and the team. What are the main takeaways for everyone listening?
All right, 3 big things stand out for me. First, massive efficiency. This IGR matches deep learning accuracy but uses 100 times less computational power. That's huge. It suddenly makes running powerful AI feasible on tiny battery-powered edge devices, sensors, wearables, you name it.
Okay, efficiency number 1.
Second, unprecedented versatility. That ultra-wideband response from nanoseconds to milliseconds is incredible. It means one device can handle all sorts of data, from super fast communication signals to slow biological or environmental changes. It's like the Swiss Army knife of reservoir computing.
Handles fast and slow. Got it. Number 3.
Third, physical compactness. They get massive computational power, simulating 160 virtual nodes out of one small, simple device using that time multiplexing trick. High power density without complex manufacturing.
Right, the orchestra trick. And thinking about manufacturing, you mentioned it uses graphene and ion gel, simple structure. That sounds like it could fit well with making flexible devices.
Absolutely. That's a really exciting implication. Because the materials and structure are compatible with processes used for flexible electronics, you could potentially see this technology integrated into things like smart clothing, bendable displays, wearable sensors that do complex AI right on your body.
So AI woven into your shirt, predicting, I don't know, your health status based on subtle signals.
That's the kind of futuristic application this could enable, moving beyond rigid chips and boxes.
Okay, that's pretty mind-bending.
It is. But I want to leave you with one last thought, kind of turning things on their head a bit.
Oh, go on.
So, the researchers noted, as you'd expect, that this device is pretty sensitive to its environment. Little changes in light, or chemical vapors nearby, or even tiny vibrations can affect how it processes information.
Right. And normally engineers hate that. They want to shield the device, keep everything perfectly stable, get rid of the noise.
Exactly, build a fortress around it. But what if you didn't? What if you embraced that sensitivity?
What do you mean?
Could you deliberately use that inherent environmental sensitivity to create? Maybe environment adaptive computing, or even multimodal computing.
So the chip wouldn't just process the data you feed it,
Mm,
it would also react to the room temperature or the ambient light.
yeah. Imagine a system where the noise, the environmental conditions isn't something to filter out, but is actually incorporated directly into the computation. Could AI become naturally aware of its physical surroundings, not because we program it to be, but because its very processing is influenced by them?
Huh. Using the environment as another input stream baked into the hardware.
Mm.
That's a fascinating twist. Something to definitely chew on.
Definitely something to think about for the future of physical AI.